So, good morning, everybody. First, I would like to thank the organizers for the invitation here. And today I will talk about the breaking of ensemble equivalence in complex networks. And this is my research project. I'm working on it together with my supervisors, Frank Denolan and Diego Garraschelli. And I'm doing this at Leiden University, both in Lawrence Institute for Theoretical Physics and at Mathematical Institute. So, in order to start talking about ensembles, I need to briefly remind some concepts coming from statistical physics. So, usually when we have to study a system consisting of a large number of particles that interact with each other, we use these so-called statistical ensembles. And when you think about an ensemble, you have to think just about a probability distribution and on the space of the configurations. And we remind two very important ensembles. One is the microcanonical ensemble, and the second one is the canonical ensemble. These are the most used ones. The first fixes the energy of the system, and so it gives positive probability and uniform probability to only those configurations that satisfies the constraint exactly, so that have the same amount of energy, while the canonical ensemble fixes the energy on average. And it uses the temperature as a controlling parameter. So more in particular, now in the next slide, I will speak more in details about these two ensembles. So more in general, you have a configuration space, Cn, where n is the number of particles, and you have also an energy function that basically takes a configurations and it gives in output a real value. And then we also fix a constraint that is represented by E star, that is a real number. And what does basically the microcanonical probability, the microcanonical ensemble, it gives uniform probability to only those configurations C, such that their energy is equal to E star. And of course, it gives zero probability to all the other configurations. What is here the problem is that we need to calculate this number omega star, omega E star, that is basically the number of configurations that realize the constraint. And sometimes this is not easy. On the other side, the canonical ensemble is the probability distribution that maximize the Shannon entropy, and it has been proved that the canonical ensemble takes the following form. That is basically the Boltzmann-Gibbs distribution. So we have an exponential term of beta star E of C, and then we have a normalizing factor Z of B star. We have to set this parameter, B star, that means basically the inverse of the temperature, and this settings basically is the responsible of the fact that the energy with respect, on average, with respect to the canonical ensemble is equal to the value E star. So what we did on graphs was to take this concept coming from statistical physics and apply this concept on the networks theory. So here we have a space of graphs, Gn, where you have to think about, for now, just simple graphs with n nodes. So there are no multiple links, there are no self loops, and we also have a vector now as a constraint, because, for example, okay, we can constrain the number of links, that is only one value, but we can also constrain more things. For example, we can give a degree sequence. And in this case, the constraint is multidimensional, because for every node, we give a constraint. We give a number of links that has to come out from it. But we can give many other kind of constraints, like number of triangles, number of wedges, or anything you can imagine. And of course, we need something that is the analogous of the energy E star, that will be a vector called C star, that is our constraint. In this case, the microcanonical ensemble will be the probability distribution that gives, again, positive and uniform probability only to those graphs such that their constraint is equal to C star. And in this case, for example, if you think about the number of links, omega C star can be easily calculated. It's just combinatorics. But if you want to calculate the number of graphs with a pre-described degree sequence, in this case, we don't have an exact number. So it can be really difficult to calculate a microcanonical ensemble. So what is the interpretation? In this case, we are modeling a random graphs, and we have partial information available through the constraint, the exact constraint. On the other side, the canonical ensemble is the probability distribution that maximizes the Shannon entropy by definition, that is minus p log p, and the sum runs over all the possible space. And this maximization is subject to two constraints. So one, of course, is that the canonical probability is a probability, so it sums up to 1. And the second is that the constraint on average, so the average constraint with respect to the canonical probability is equal to the value C star. So this is solved, and the solution of the system is, again, a Boltzmann-Gibbs distribution where you have exponentially of an Hamiltonian, and on the denominator you have a normalizing factor. And the Hamiltonian is just the product of the Lagrange multiplier theta and the constraint C. Z of star, as I said, is the normalizing constant. It is the responsible of 1, while when we set the value theta star to the real value, then we satisfy the second equation here. The interpretation here is that now we model a random graphs with information available only the average constraint. So microcanonical and canonical ensemble, they model two different type of networks in this case. And there is a big question, so when they are equivalent, can they be equivalent, and in which sense? So we give here a definition, and we say that the microcanonical and canonical ensembles are said to be alpha n equivalent when their relative entropy divided by alpha n is going to 0 when the number n of nodes goes to infinity. So here, the relative entropy is the sum of microcanonical probability, logarithm of the ratio of microcanonical probability and canonical probability. And as you can see here, this is not a distance, is not symmetric, but is a pseudo distance. And it makes sense to write this because the microcanonical distribution is absolutely continuous with respect to the canonical distributions. So we don't have problems like canonical probability equal to 0 and positive microcanonical probability. And one very important simplification that it's really useful in this context is the following. So when we work with graphs, relative entropy can be simplified, and we just need to calculate the logarithm of the ratio of microcanonical and canonical probability of a particular graph, that is G star. And G star is any kind of graph that satisfies the constraint exactly. Of course, this exists because when we define any kind of model, we will start with a constraint that is realizable. Otherwise, it doesn't make sense to talk about number of configurations and ensembles. And in the following slide, now I will explain why we use the relative entropy as a measure, and in which sense, what happens when this is going to 0. So what does they mean, these two ensembles? The ensembles, microcanonical and canonical, so as I said, they model two different things. And the microcanonical models a complex networks in which the constraints are hard. So it only wants to give positive probability to those configurations that realize the constraint exactly. And this is a way of studying a complex network. But in the canonical ensemble, we allow more freedom. So we can pick a graph, and even if this graph doesn't satisfy the constraint exactly, it also has some probability. And there is an inequality coming from Pincer, and this basically is saying that the total variation distance between microcanonical and canonical probability divided by square root of alpha n is not growing more than the alpha n relative entropy divided by 2. And this is really important because it links distance with absolute distance. And from here, we know that if the alpha n relative entropy is going to 0, then the total variation distance is not growing more than the square root of alpha n. So we understand that in some sense, if there is alpha n equivalence, then the distance between these two ensembles is not growing too much. And so it let us know how much mistake we commit if we use one ensemble instead of another one. There is also one last very important fact, that is that in many statistical physics textbooks for interacting particle systems, it is said that the two ensembles are n-equivalent, while this usually is not true. It's not true in every case. There are many counterexamples, and it is basically what we are going to show now here in this presentation, in this work. So I will start now with the first example, and is called fixed number of links, because we pick a simple graph. So we have a set of vertices, a set of edges, and what we write as a constraint here is the number of links, L star. So it's a one-dimensional constraint now, and this number of links is can be written as lambda mn, where lambda is basically representative of the density of the links, while mn stands for the maximum number of links. That of course is n choose 2, because we have a simple graph. In this case, microcanonical ensemble is really easy to be calculated. It's just binomial coefficient. So from combinatorics, we can immediately know how many graphs I can draw with a prescribed number of links. And so basically, the microcanonical ensemble will take this number to the power -1, and only for those graphs that have a number of links equal to L star and 0 to all other configurations. The canonical ensemble, on the other side, takes an Erdős-Rényi form. And what is going to happen is basically that the canonical ensemble of any graph G in the set of graphs has probability p theta star to the power number of links and 1 minus p theta star to the power number of non-links. And this probability, p theta star of connectance, is the same probability for every pair, and is basically taking the value lambda. I will show here now all the calculations, and I will do this just for these first examples, because it's the simplest one and is maybe better to see how does it work, the calculation of canonical ensemble and of the relative entropy. So in order to calculate the canonical ensemble, we need to calculate the Hamiltonian, and the Hamiltonian, by definition, was the product of theta and the number of links. And the number of links can be written in this sum, so sum over all possible pairs of Gij of G, and this Gij is the adjacency matrix, so it's basically 1 when there is a link between I and J, and it is 0 when there is not a link. And after that, we can compute the partition function. And basically, this is the sum over all possible graphs of e to the power Milton. And there is a trick here at some point. This sums becomes a product here. And we can exchange the product and the sum. Only in this case, because basically there is only one interaction per time. This can be done whenever the constraints are linear, but is not doable when, for example, a number of triangles. But this clearly simplifies the computation a lot, because then now we can compute exactly how much is the partition function, that is 1 plus e to the power theta, product over all possible pairs, that is n choose 2. So with now the Hamiltonian and the partition function, we can put these two ingredients into the formula of the canonical probability. And what I write here is the canonical probability of a graph G depending on theta. Why? This is because theta has not been set yet. We will do this later, and we will set it in such a way it respects average constraint equal to the real constraint. So what we do is basically writing again, taking the formula of the canonical probability and putting the partition function here and e to the power Hamiltonian here, the product goes out, and what comes out is the formula in before, p theta to the power links and 1 minus p theta to the power of no links. And the p theta takes this form, e to the power theta and 1 plus e to the power theta, that is a number in 0, 1. And then, since the average number of links with respect to this probability distribution is basically p theta mn, and the number of constraints is lambda mn, then we get immediately that in the value theta star, in the correct value, we have p theta star equal to lambda. After that, we can easily put canonical and microcanonical into the relative entropy. What we obtain is something that in the limit is going to 0. And then, so we have, in this case, an equivalence of the ensembles. But this was a really simple case. We only had one constraint. And what is interesting is to see what happens when we put more constraints on our model. And this is what has been done in the configuration model. So here we have again a simple graph, but what we do is basically per vertex, we say the first vertex you should have k1 star nodes, the second vertex k2 star nodes, and the last vertex kn star nodes. So we are basically giving n constraints because we are giving one constraint per vertex. And so this number is growing linearly with the number of nodes. And as you will see here now, this will have an effect, a really big effect on the equivalence of the ensembles. So in order to see the calculation, we need to give two definitions. And the first is this Fn, that is called empirical degree distribution. And it is basically saying Fn evaluated in a number k is giving me how many nodes of this k1 star, kn star has a degree k if I divide this number by n. And on the other side, we want to define a norm, that is the norm of f in L1G, and is basically the sum over all possible numbers of f of k, g of k. Now, this function's g has an interpretation, is basically the logarithm of the inversion of a Poisson random variable of parameter k, calculating in the point k. And we need also two assumptions. So at first, we need to be in what we call sparse regime. So we need that the maximum degree is not growing more than the square root of n. And we also need that the function, the norm of the function f in L1G is finite. So it should exist a function with this property. And the limit, so the norm of fn minus f in L1G has to go to 0. So basically, it should exist a function such that this is the limit in the norm of the function of the empirical degree distribution. And after these definitions, we can calculate actually the microcanonical ensemble. So as I said before, for the configuration model, there is an exact formula. So we don't know how many graphs there exist with a pre-described degree sequence, but luckily there is a result coming from Bender, and it says basically this number, we don't know how much is it, but it's growing with this factor, and something that is not growing more than the square root of n. And this is really useful in our context because, as you know, we have to calculate the relative entropy, and so we have to take the logarithm of this and divide this by alpha n. So whenever alpha n is bigger than n, this error term will be, in the end, small of 1. And on the other side, the canonical ensemble becomes this time an inhomogeneous Erdős-Rényi random graph, and so the canonical probability will become product as Pij to the power Gij, 1 minus Pij to the power 1 minus Gij, and we do the product over all possible pairs. This time, the probability of connectance Pij is more difficult to be calculated, so we need, again, to satisfy average constraint equal to real constraint, but with this form, it is impossible to calculate exactly the values theta I star and theta j star. So what we did was an approximation, so we are saying here, oh, this probability, Pij star, are probably not growing too much. They are really close to 0. And so we say this denominator, 1 plus e to the power theta I plus theta j, is very close to 1. And so this is why we approximate the probability in this way. If we do this, then the problem is solvable. We immediately see that with the correct value, theta I star and theta j star, we get this probability of connectance. And there is only a question, is this a good approximation? Of course, the answer is yes. This regime Pij star can be approximated in this way. And the idea is that since the graph is sparse, there is not much connectance, and it makes sense to suppose that the probabilities are very small. And this is also, it has been proven mathematically. So it has been proven that if we take these probabilities and we plug them into the canonical ensemble, and we calculate the relative entropy with these probabilities and with the all probabilities, we basically obtain the same result. So what happens here in this case is that we break the n-ensemble equivalence because the limit of the relative entropy this time will become this function, this norm of the function f that is positive. And here we started thinking so that probably the responsible of the breaking of ensemble equivalence was the fact that the constraint was bigger, was growing with the number of particles linearly. And so what we did was to study the same constraints in the bipartite graphs. And so again, what is a bipartite graph at first is a graph consisting of 2 layers, the top layer and the bottom layer, and only links between the 2 layers are allowed. There are no links intra-layer. And in this case, we have here m nodes, and in the bottom layer, n nodes. What we did so was to fix at first the number of links and then the number of degrees, so the degree sequences, and see if it was leading to the same result. And so, again, in this first case, the number of links is represented by lambda mn, where lambda, again, is the proportion. And the microcanonical ensemble was taking this form, again, positive and uniform probability coming from combinatorics, only to those graphs that have a number of links equal to L star, and 0 otherwise. The canonical ensemble, again, is taking an Erdős-Rényi type form, And what happens to the relative entropy per node is that it is going to 0. And so we have m plus n equivalence. On the other side, if we constrain the degree sequence, things change again drastically. So I give here S1 Sm to the first layer, I give T1 star Tn star to the bottom layer, and again we suppose that the regime was sparse. So the graph was not too dense. And the relative entropy this time becomes again positive. It is basically a mixture of the norms of the two functions f12 and f21 that are the analogous of the one defined before, with a weight a1 and a2 that are basically the proportion of the nodes in the first layer and the nodes in the bottom layer. So we have again m plus n non-equivalence. So with the third case on the bipartite graphs, we were basically convinced that the number of constraints were playing a role. In fact, what we did here was basically to constrain only the top layer and leave this bottom layer free. And again, we need the empirical degree distribution. We need that it converges in the normal 1G to some function f. And here, in this case, we don't need any assumption on the regime. The regime can be anyone, and sparse or non-sparse. Microcanonical ensemble and canonical ensemble will be calculated exactly. And what happens to the relative entropy per node here is something really interesting, because this time it goes to A1, norm f L1G, while this norm is every time positive. But the factor A1 can be 0 or not. And this means that we have two possible regimes here. So in the first case, when A1 is equal to 0, we have equivalence. But if A1 is positive, and then we have non-equivalence of the ensembles. And what is the physical idea behind this? So whenever the number of constraints was growing with the number of nodes, so when A1 is equal to 0, then this means that m divided by m plus n is going to 0. So the number of constraints divided by the number of nodes is going to 0. And then we have equivalence. While if the number of constraints is growing like the number of nodes, so m is growing like m plus n, we lose the equivalence. And then afterwards was our goal was to study, of course, the dense regime, because there were no results about it. And this was doable in the configuration model and in the simple version, so in the when we have only one layer. So here we define the dense case in this with this definition. So we say that a degree sequence is delta tame when it exists a number delta such that the connectance probability coming from the canonical ensemble are bounded between delta and 1 minus delta. And maybe this doesn't tell you anything, but you can see from this equation that delta tame regimes basically means non-sparse. In fact, if you sum here with all possible j not equal to I, you see immediately that here this becomes ki star, and on the other side you have n minus 1, 1 minus delta, and n minus 1 delta. And this, of course, means non-sparse, because if you divide this number, you see immediately that ki star is growing like n. And the result in this case is that the relative entropy with alpha n that is slightly bigger than the one before. So when alpha n is equal to n log n, it becomes 1/2. And so what we can say here is that the relative entropy, so we have divided by n log n, is leading to n log n non-equivalence. So in conclusion, we can say that whenever the number of constraints is extensive in the number of nodes, we have two cases. In the sparse regime, the breaking of ensemble equivalence occurs with alpha n equal to n, while in the delta time regime, it occurs with alpha n equal to n log n. And of course, for the future, we have some plans. So first is to study the breaking of ensemble equivalence in other regimes. Because, okay, we said what happens in the sparse and in the delta tame, but there are regimes in between that are non-sparse and non-delta tame. And another plan is to study what happens with different constraints. And this is what we did with Nikos. If you followed his talk of 2 weeks ago, he talked about the number of triangles and dense regimes. And here you can see that the things changed drastically. With this, I conclude, and I thank you for your attention.
So a general question that we have is that how would we all put this in a bigger large deviation framework? Because Hugo has an in which for physical systems of particles under some assumptions of the existence of LDPs, that breaking of ensemble equivalence is related to non-convexity of certain weight functions. In Nikos' talk, there are weight functions appearing which come, but that have to do with this Chatterjee Varadhan large deviation principle. Here in this regime, you don't see rate functions, but you sort of smell them in the background. So how do you have a large deviation view on the sparse regime in the spirit of what Hugo did?
Yeah. So this work is basically a lot of combinatorics. So we never had the possibility to use large deviations on it. And I don't even know if there are results about large deviations with the sparse regime, because all the results we saw and we used were about the n squared case, so when the regime was dense. And probably, maybe there are results, and maybe this can help, but I have the impression that now the sparse regime is already completed, and probably there is no need to use large deviations.
Yeah, so recently I heard instance where you had constraints, and if you want them to satisfy in the hardware, as you say, then it was impossible because they were like system with two conserved quantities.
You mean in the last, in this case, where you have two possibilities, or?
No, I mean this is a system that was a system with it was another physical system, but that you did not talk about, right? So
okay.
The question is about something slightly different. But so what I remember there was that it was possible that if you want to satisfy them in a hard way, it was impossible just because sometimes you cannot. If you want to satisfy them in the soft way, it was possible. And then I wondered whether this could fit into the non-equivalence of ensemble, or this is something different.
So what I say here is not that this is possible or not possible, but that microcanonical ensemble and canonical ensemble are modeling two different type of complex networks. And sometimes microcanonical ensemble can be harder to be calculated because you need to count and you need to know exactly this number, while canonical ensembles, usually it's easier to be calculated. But yes, in this case, the question is, suppose that, for example, we want to use the canonical ensemble instead of the microcanonical ensemble, how much error we commit. And this is basically what the equivalence says, because if here you can see if here we have equivalence, then we know something about the distance. And so we know something about the mistake we do if we use one instead of the other. But yeah, they model two different things. So if one wants to be precise, is to use the microcanonical ensemble if the constraints you put are hard, or the canonical if they are soft.
Can you come back to the... Is this working? Yeah. Can you come back to the definition of the entropy, please?
Yeah. Here. The Shannon entropy or the relative entropy?
The relative entropy.
Okay.
Sorry. Yes. So so if you have, in relation to the previous question, if you have a microcanonical ensemble which has probability, which doesn't have any configuration, the probability is 0 everywhere. So this is exactly 0 because P mic is just 0. In that case, they would be equivalent because the relative entropy is 0.
So I mean,
or am I missing something?
Then it doesn't make sense to talk about it, probably.
Okay, but it's still.
So I mean, you have to have at least one graph that satisfy the constraint. So for the graph, for example, if you give a degree sequence that is not graphicable, then it doesn't make sense to study it.
Okay.
Other questions? Thank Andrea again.
Thank you.